One-dimensional motion. And we started the year by looking at one-dimensional motion that was constant rate motion. Then we said after that, what if the motion is accelerated? What if it speeds up? Or what if it slows down? That was the second part to it. Now we're going to say, now that we have accelerated motion and constant motion, can we look at motion that is launched at some sort of an angle? Okay? Or can we look at motion that's launched horizontally, but then starts to fall towards the ground? So we're going to incorporate this section, this topic, for a couple of days we're going to spend on this topic. We're going to incorporate gravity in the vertical direction, just like we have been, right? For the free fall problems we've done now, or the launch straight up problem where gravity pulls it down. Now we're also going to incorporate constant motion in the horizontal direction. Because when an object is fired horizontally, gravity is the only thing pulling it down. It still wants to move left to right the whole time. Now, air resistance does have a tendency to slow things down, but we're going to look at problems that don't involve air resistance. Then we're going to maybe later on say, what if air resistance is included, like on your test, right? When I said G is now 3/4 of G because we're taking into account air resistance. That's not the traditional way you would do it, because air resistance doesn't just affect G, it affects a couple other things actually. But that was a simplification of that idea. So we're going to do that a lot in this section. Now, to start, what I want to do is a quick demonstration. And I want to show you this apparatus first because we're going to use it a couple times this year. Now, we're also going to use simpler apparatuses, and we're also going to look at like computer simulation. But projectile motion is not the easiest thing to really study in the lab because, again, we need to launch projectiles. So we might go down to the gym for a day or two to look as well. So the way this apparatus works, and you can probably hopefully see from where you're sitting, I'm trying to hold it up a little bit here, is there are two buttons here first, arm and launch. You have to press both, kind of like you see those old movies where there's two keys to launch a nuclear missile or a nuclear warhead. I'm trying to make the same idea, but you need to press both. This puts pressure in the line. So you'll see there's a pressure gauge right here, barometer, pressure gauge on the side of here, and you can pump more air, compressed air, behind where the projectile is waiting. So there's one projectile here, and there's another projectile sitting right here on the side. This one is just sitting on a little hole inside it. It's just kind of sitting on this rest. Okay? Now, we can angle this, and you'll see a protractor here. In a little bit, we're going to do that. Not today, but in a couple of days, we're going to see what happens if it's angled. Now, in addition, they also give us what's called an internal photo gate distance here. If you remember the photo gate we did with the picket fence, remember you dropped the picket fence and went through that little photo gate? There's a photo gate in here that is exactly 5 centimeters. Same distance between those bandwidths, if you recall, from the picket fence. The idea is that it can measure the position of a projectile 2 different times, and therefore calculate and approximate what we call muzzle velocity, or initial velocity. So the photo gate allows the computer device in here, when connected, which I'm not going to connect today because we don't care about it actually today. When I connect it to the Vernier device, it'll give us the initial velocity with which it was launched. The angle can be measured here with the actual protractor. The amount of pressure simply affects the initial velocity coming out of the actual muzzle, or out of the rifle, we should call it. The rifle is just the actual chamber itself. Not a real rifle. What else? Now there's a nice level on the front. The reason for the level here is so that you know when you're launching something horizontally. Today's concept is going to be about launching things horizontally. So this needs to be perfect. And I already tested it out because it's wobbling right now because I'm moving my hand. But this little air bubble here will be centered in the middle that tells you that it's level or it's on level ground. And I can adjust this by tightening or loosening these two knobs here and then adjusting the angle at which it's launched. So we're going to do a lab together as a group in a couple days. You're also going to do a couple simulations on a computer with a program, and we're probably also going to go down to the gym. So we're going to do a lot of different different types of labs for this. But when we do this one, we only have one of these devices. I can't really get 5 of them to launch across the room because it gets crazy. So when I do this, I kind of just do a demonstration with this one. So for today, I'm going to quickly demo what we're going to be talking about for the beginning of the lesson. I'm trying to think anything else here. Is this page? No, it should be good. So on the back, they also give you a little diagram here, and it tells you the launch point. So usually, without this little barrel here, the launch projectile is actually contained inside of here. I can show you what I mean. This comes right out. So let me grab it. So the projectile is normally in here, okay, and it gets launched out. But because we're using this one today, okay, we're going to launch one on the side as well. Thank you. So the projectile is currently only right here. But normally, it goes all the way back here. And that's the reason with this diagram. So you know what the initial height is, you know what the initial displacement is, and it's all given in centimeters. So that when you look at y0 and x0, you have the correct coordinates for your initial positions. Okay? So I'm just going to move over here on the side for a minute. Okay. Now, what I want you to think about is this. If you know the answer, you don't have to be like spoiler about it, but maybe talk to the person next to you for a moment, which I'm going to have you do. You don't have to call out the answer if you've seen this already. But this projectile here on the inside is going to be launched horizontally. This projectile that's right here, as soon as this one is launched, this little metal bar is going to retract. And as this bar retracts, this object's going to be dropped. So I used to do this with some tennis balls earlier on in the year. And the tennis balls work, but they're not as precise. And what we would do with the tennis balls is one person would roll a tennis ball, and as soon as he got to the end of the table, the other person would drop the other tennis ball, as the first one was exiting the table. So when it was like right here at the very edge of the table coming off, and it's going to fall in this pattern, right, in that arced curve or parabolic curve, the other ball was dropped. And the question was, discuss what's happening in the problem. So before I do this, spend a minute, literally a minute, talk to the person next to you. What do you think is going to happen with these two projectiles? That's the question. Okay, spend literally a minute talking. Good. Arguments. What do you think? As a result of your conversation, what do you or your partner think, or did you differ in opinion? What do you think is going to happen? Who wants to give some sort of statement? Nick?
Do you think the balls are going to hit the floor at the same time?
Okay. Nick thinks the balls are going to hit the floor at the same time. Do people disagree, agree, simply show of hands if you agree with Nick? If you agree with Nick. Okay? If you disagree with Nick, what's your opinion? If you disagree with Nick, what's your opinion? Remember, there's no wrong answer right now. Okay? There really isn't a wrong answer. You're taking a hypothesis. That's what science is about. So if you thought something different, please give that information. Okay?
I don't know, I thought they might hit it at different times just because one has just a straight line to travel and the other one has to travel in a curve.
The second one has to travel further, the first one falls straight down. Okay? What else? Yeah?
Yeah, I thought that maybe they hit at different times because one has velocity going this way while the other one is just going straight down.
So one's a free fall and one has velocity to it. Yeah, good ideas. And the idea behind this is that there isn't a right answer until you see it happen, right? And then we'll talk about why what happened, because that's what's more important afterward. So some of you might know, oh, if I think about the math behind this, I can figure it out. And there is a lot of math and physics behind what's happening here, and you can determine that answer. But we're going to show it first as a demonstration. So give me 1 second. Make sure this is nice and pumped. I want you to assist those hands here. You notice the thing moving? Okay, so here's what I want you to do. You can kind of stand and go to look, but you really need to listen, okay? Because they're both plastic marbles, so you'll hear them hit. So the goal is to listen, okay? That's good. I want to make sure everything's right. Okay? 3, 2, 1. Hold on. I think this needs to be plugged in. Now, it should have to be plugged in. Hold on. It should have to be.
No one's expecting it, so someone gets like a concussion.
I think it's not launched.
I think so. It like bounces off and breaks the window.
Ah, there we go. Okay. I think that was all that.
That's my hypothesis. It will break a window.
Alright, try one more time. 3, 2, 1. Let's try one more time. So, by the way, I want to point something out. Nick, can you come to the front and help me with something? Nick, where do you think that? I saw you standing. That's why. Do you see where that is approximately? Give me a spot. Yeah. Okay. So stay around that area. It's not going to take that long. I mean, my, so that's where it landed, the first one, right? The second one that dropped landed directly below it. So I want to see if this is going to land it. But again, listen, okay? 3, 2. What are we hearing? What are we hearing? It's tough, right? I'm going to go a little bit slower. Yeah, if you get a video, it would be great. Put the wrong one in. Hold on, hold on. It's not, that was not the work. I put the wrong one in. There's a little like hole on the side, or else it won't work. Yeah, Nick, if you can get a video from the ground, that'd be great. So I'm purposely not going to pump it up too much this time. Okay, I launched the first one a little further. The second one, maybe like halfway across the room. Ready? Yeah. 3, 2, 1. Let's do it again. Let's do it again. Again, why am I doing this over and over? Because if it were me and I were a student and I didn't know the answer, I would run trials, right? To really see what's happening over and over. If I'm not sure, I would keep running those trials and maybe vary stuff along the way that I needed. So what is my variable right now? What do I keep varying?
The pressure.
The pressure in the line, which then varies the
Initial velocity.
initial velocity. Okay, so I'm seeing what the initial velocity has an effect. All right, Nick, here we go. 3, 2, 1. Any conclusions by now? Next, a couple enough trials here? Nick, did you get a good view of that?
Yeah.
Can you airplay from your phone?
Yes.
Can you find physics lab on your phone? I might have to disconnect mine. Hang on. Let's take a look at it in slow-mo for a second.
I do too. We need to sing a lot.
All right, take a look.
This soundtrack is ridiculously hard. Let my people go. Stop insanely hard. Val Kilmer plays both God
Help me
and
find the discoverable. Yeah, hold on.
anything comedic about that. I don't know exactly.
Okay, look for Mark's.
Sandra Bullock, Nigeria.
Regina, getting it. Sorry.
No, the animated movie that we got
Mark's not
it's
good.
Oh. Just gotta be the way.
I like to get the
249. All right, let's take a look at the video real quick. Nick's going to show it to us. Can you turn your phone? Is it turn horizontal?
Oh, okay. Nice view.
All right, here we go. Let's take a look. Follow the. We should have done it with a black background. I didn't realize it's not going to be tough. That's your way. Maybe zoom out a little bit. Yeah. So you want to see the floor? Nice. So we see one of them about to the floor. Where's the other one now? Oh, okay. Get it right with this again. Ready? Set, boom. Isn't that awesome?
That's really cool.
It's not something you'd expect either for the reasons you all stated. One has velocity, one doesn't initially. You have to hit the ground. Now, the crazy part is, I don't know if you picked up on it, depending upon where I launch it, there is a small discrepancy, and you said it the first time. The first one I launched, like almost at the podium, Caroline goes, it was close, but I think it was actually a little off. And she's right, it was a little bit off. Why was the first one slightly off, and the other ones were much better runs? Jack, what do you think?
Because the further it goes, the more air it's like running into.
Yeah. Air resistance affects things more the longer it's in the air, or the further it travels. So as a result, the first one that was launched all the way here was being slowed down by air resistance more than the other ones that were landing over here. The one that was a free fall was practically not being slowed down at all, but hitting obviously for this much distance, right? But this one is traveling through the air. The other effect, Morgan.
So if you increase the higher the initial velocity, the less equal it will be, or
The higher, yes, correct. The more initial velocity, the further it's going to travel, the more it's in the air while moving horizontally. Motion is what creates air resistance. Do this real quick. Take your hand like this. Okay? And just don't hit the person next to you. Just move it like this very slowly. Very slowly. Now do this. Ready? Now, move it a little faster. And you show a little coil, right? Now do this. Turn your hand, and then go. So it's perpendicular body. Then do it. So if you do this underwater, it's not as obvious right now because the fluid that we're submerged in is oxygen. Well, a combination of that. But the fluid that we're submerged in does not create much of a viscous force because it's not very dense. If you've done this before in the pool or in the ocean, you can literally feel a lot of resistance when you do this. Not as much when you do this. And if you move really slow, you barely feel any resistance at all. The air resistance or fluid resistance is a function of your velocity and your area, the cross-sectional area in contact with that fluid. So if I move faster, higher air resistance because I'm moving faster. If I turn my hand like this, higher air resistance because, again, my hand has more area when it's turned this way. So in the examples that were launched further, it was traveling at a higher velocity. Higher velocity meant more air resistance, which is what makes the further launches not as good of a demonstration as the shorter launches themselves. Now, let's go into, we're going to see now, why this is all true. Next thing.
Yeah.
Let's go into why this is all true today, because that's really what's way more important. Like, we can see it, and that's great. And science is like, half of science is empirical, right? Where you look at stuff, you study things, you look at relationships, you recognize, like in chemistry last year, for like the gas constants and stuff, they're not just made up. They're determined from experimentation. The same concept applies here. There was definitely a time where people didn't have a device like this, and they did exactly what I was saying earlier, where they literally grabbed two tennis balls and tried the same thing. One ball was rolled off, one was dropped, and they hit the ground at approximately the same time. Now the problem with that is what?
When were tennis balls?
Two tennis balls, yeah.
When were tennis balls invented?
Oh, that is the problem too. Any object would work. I like that answer. When were tennis balls? What's the problem with that in general, though? That experiment was the problem, if I'm saying. What do you think? What's the problem? Christina?
It's good if you're throwing it yourself because you vary the amount of initial velocity you put on it.
Yeah, there's human error involved, pretty much, right? I'm going to roll this object to the table, that's fine, but the person waiting here has to time it. Like, ready, set, drop. Like, how do you know that this is being launched, meaning it's exiting the table, at the same moment you're dropping it? There's a lot of room for error there. So having this device here, if you notice what happens, when this projectile is launched, there's a little nubby here. It's not the size of the word, a pin. There's a pin here. Hold on. Okay. So take a look. I know it's tough to see, but look over here. For a close-up, you can probably see if you maybe stand up. There's a pin on the side. When I put this one projectile in here, the other pin comes out. So when this projectile gets launched, the pin retracts at the exact same moment. And this projectile has a little hole in it. So this projectile is literally sitting on the pin. So I take this projectile and rest it so that it's sitting on the pin. When this one falls out, the pin retracts. At the exact same moment, it drops the second one. So these two projectiles are launched at the same moment. To do that experimentally and like just walk in and trying with tennis balls probably wouldn't work too well. Okay? So let's talk about now why this is true, why what we're seeing happening is actually happening. So we're going to start by looking at projectile motion. We're going to start by looking at projectile motion here. And the idea behind projectile motion is this. Any object that's under the influence of gravity, while traveling horizontally, is considered a projectile. And that's probably actually on the next slide if we go ahead and take a look at that slide there to see. Yeah. So a projectile, again, is projectile itself is any moving object. You model as a point, a physical point in space. But projectile motion has to have some sort of vertical velocity with some sort of horizontal. And the vertical velocity doesn't have to be in the beginning. It could be, like we said, a free fall. So a free fall itself, I just dropped this, right? That's just one-dimensional kinematic motion. But when we launched the object instead, it was only launched horizontally. So we would say it only has velocity in the x direction to start. But what happens as it falls toward the ground? What happens as it falls toward the ground? What do we think? So it only has horizontal velocity to start. But as it falls toward the ground, what do we think is happening? What do we think is happening? Just let me look at it. Gravity, I like it. So, as a result of gravity, You're on the right track. It has acceleration, gravity. What does gravity do? What does it cause the object to do?
Move in the negative y direction.
Move in the negative y direction. So although this was only launched with velocity x, what does it pick up along the way? It picks up vy, vertical velocity. So these problems that we're going to start this chapter or this section with are going to be launched horizontally. That's what today's focus is going to be. Then, after a couple days, after we do a demo or so, we're going to take, or a lab or so, we're going to take a look at launched at an angle. And you'll see that at the end of the homework, we didn't specify which is which. Okay, you'll notice that a little asterisk. The ones with the asterisks are launched at an angle. You're going to do those later, like next week or over the weekend. This kind of stuff we're going to take a look at today. So when you're practicing the homework, you're going to do horizontally fired projectiles. Now, the person in the diagram is a track star running with horizontal velocity. Then this person jumps. When the person jumps, the person gains vertical velocity and had horizontal the whole time. And when this person gains vertical velocity, this person is then going to lose vertical velocity and come back down. Or it's going to slowly lose their velocity, get to the top, stop moving vertically, and then start to fall back down. The same concept as the max height problem. The max height problem is so important, and I kept saying that. When it gets to the top, what does it do? It stops. That's why we kept setting v equal to 0 for max height problems. The same concept applies when this person reaches max height, but it's only the vertical velocity that's 0 there. The horizontal velocity, well, that part, that's going to be the same the whole time. Why is this never going to change? Why is the horizontal velocity of the object or the projectile never going to change? Jack, what do you think?
Well, since we're assuming, or like not including air resistance, there's nothing to slow down.
There's no decelerating or accelerating entity, force, that's causing it to change horizontally. What's changing vertically again? What'd you say, Justin? What was it vertically? Yeah, it's just gravity, right? Pulling it down. But if you throw something like a baseball, gravity pulls it down. So a baseball, although seemingly horizontal when a pitcher pitches, or a softball pitcher pitching, is not actually horizontal, perfect. It drops. And we're going to see in this chapter the idea of like, if you take a bow and arrow and you launch it, the further away you are, the more that bow and arrow is going to drop toward the ground. So that's why, if you know, like in like those movies, what's the movie? What is it? No, it's with Bradley Cooper. He's a sniper. What is it called? American Sniper. Is that what it's called? American Sniper?
Yeah, I think it's called American.
Yeah.
Anyway, in these, it's not Bradley Cooper.
I think Bradley Cooper was in Lone Survivor.
Sorry, yeah. Anyway, so some actor, whatever. I used to reference Kiefer Sutherland from 24. Did anyone ever watch the series 24? It's pretty awesome, actually.
Still watching.
It's really
The
awesome.
last survivor.
Anyway, so when a sniper were to shoot, or when somebody were to shoot a bow and arrow at a long distance, if I wanted to hit the cabinet, which was eye level with me, I can't just release. I have to angle it up a little bit, right? Because I have to take into account the fact that there's going to be what's called drop, or object drop, or bullet drop is a phrase. Okay? Anyway, the concept here is that it's moving vertically due to gravity, but horizontally, it's never going to lose or gain velocity. We're going to assume no air resistance for now. So, we have an image here of a soccer player heading a soccer ball, right? And there are two paths taken here. The path A is the idealized path. If path A is the idealized path, what would path B be? What would path B be? The realistic path, okay? So realistically, what we notice for these, we notice that the projectile itself will be parabolic and will have perfect symmetry with projectiles. But if it's launched with some air resistance, it's going to slow down along the way. So trajectory B is literally just slowing down. Oh, we should just happy birthday to her.
Do it.
The kids had a question. They were asking about bio. I don't know.
Yeah.
They were asking something about bio.
Happy birthday to you. Happy birthday
Oh, somebody knows it.
Happy birthday,
She doesn't want attention. Thank you. That's nice. So the projectile in part B does feel air resistance. So we're going to look in this section about, we're going to look at symmetry a lot. And when air resistance is accounted for, we're going to lose that symmetry that we have. But without air resistance, the idealized motion or trajectory is following path A here, and we would see symmetry in the parabola. Just like in your math courses, when you graph parabolas, you have an axis of symmetry, and at the axis of symmetry is where the maximum height occurs, or with a parabola like this, is where the minimum occurs. The same is going to occur here in our projectile motion problems.
Does this only work for objects that are spherical or like?
Yeah, so the idea is that the shape of the object would affect air resistance.
Yeah.
So if we assume there's no air resistance, which we're going to do, the shape doesn't matter.
Okay.
But the closer it is to a sphere, or the closer it is to a streamlined shape, then it would have less air resistance. Yeah, but if you took a cube and tried to throw it, it would have a lot more air resistance. It would be tumbling at different angles. The air resistance would change as it changed its rotation, so there'd be a lot more to it.
Or if you take like a badminton.
Correct. Or like a beanbag or something like that. You throw it where it topples on itself or it rolls over.
If you like throw it and you had some like spin to it, is that gonna mess it up as well?
Yeah, so when you spin something, it gives it rotational energy. So some of the energy that goes into your throw will go into the spin. Now, the spin itself would definitely affect the amount of air resistance it feels as well. A bullet coming out of a barrel of a rifle, it actually rotates like this the whole way. So the shape of a bullet, say this is the bullet itself, it's a long bullet, right? But it rotates like this as it's spinning. The inside of the barrel of a rifle is rifled. That's why it's called a rifle. The inside of the barrel has cutouts in it that are actually making the bullet rotate like this. If the bullet weren't rotating like this, you wouldn't fire in a perfect line. That's why if you look at old movies, when they use muskets, what did muskets have? They didn't have bullets, they had musket balls. Yeah, they were literally like what we saw there. And those musket balls would just be launched out the end of the barrel. And the barrel, the inside, had a ton of impurities. There would be stuff in the inside of the barrel that wasn't smooth. So a musket being fired from here might end up there, it was never reliable, which is why in a lot of wars people end up like, yeah, you have to push it all the way down. But even when you did that still, the barrel on the inside was not smooth enough. So it would create impurities as it was being launched, or it would create defects in a sense. So you never had reliability. Now, obviously, with different types of weapons, it's different, yeah.
So the difference between A and B, so A, it's obviously the Y max value is higher, and the X because it'll travel further. But does A, like the force is greater because it goes further, or what's the difference between the two?
No. So in part B here, all that's happening is as it's traveling along the path, wind resistance is pushing in the leftward direction. So this projectile that wants to go this way is being pushed back slightly by air resistance, so it's not going to go as far in the X direction. It's also not going to make it as far up to max height as it would without air resistance.
So A is without air resistance, B is with air resistance?
Correct. B is with air resistance, A is without air resistance. Yep, very good. All right, so let's take a look at this, and let's take a look at an image so you can see what's physically happening. So this was exactly what we just did. Okay, this is literally what we just did. In the very beginning, this object was launched only with horizontal velocity. Only with horizontal velocity. And what we see at the very top here is that, look, our velocity is only VXO. Velocity in the horizontal with the O simply meaning initially. Velocity in the horizontal initially. And then what happens, as you notice, as I think Mauro mentioned, or I think it was Mauro that mentioned, we're adding velocity in the vertical direction. Now what's happening to the vector length? It's increasing. Because again, gravity is causing this object to accelerate toward the ground. And because it's accelerating, acceleration causes a change in velocity by definition. Acceleration is a change in velocity. So the Vy vector is increasing in length as this projectile falls toward the ground. What do you notice about the Vx vector? What do you notice about the Vx vector? It stays the same. Anybody think about why that is again? What did we just say? Why is the Vx vector not changing? Right, here it is. It's here again. Again, it's there. The Vx vector is just not changing. But Vy is. Again, what's that reasoning? What's that rationale? What's the rationale again? Come on, I'm seeing the same hands all the time. The same hands. George, help me out.
Because there's no acceleration on it.
Thank you. There's no acceleration in the x direction again. We're assuming no air resistance. Look at the acceleration in the diagram. It's given at the very top here. Acceleration is equal to g and it acts downward. You're told at the very top. So that's why the Vy component is consistently getting greater and greater in velocity. And take a look. This is our image. This is the one that was dropped. See it dropping? It's falling. It's falling. It's falling. And look, they're falling at the exact same rate. This was what Nick just took a video of, literally happening until at the very end, these two projectiles both hit the ground at the exact same moment. Okay, what's the only major difference here? Is that one of them gains horizontal displacements. One of them, because it's launched this way, gains horizontal. The other does not gain any horizontal displacement because it was dropped. And look at the length of this vector here. The y velocity here is the exact same velocity as this velocity. So again, these two, let me point so you can see them. This velocity here and this velocity over here are the exact same value, these two right here. Over here, these velocities are the exact same two values. So as an object falls toward the ground, it doesn't matter what's happening to the x velocity. It means nothing to the y velocity. It means absolutely nothing. Okay, the y velocity changes only because of gravity. The x velocity does not impact the y velocity here. So when we look at these problems in this section, because the velocities don't affect each other, we are going to specifically look at the directions separately. We're going to look at the x direction, and we're going to look at the y direction, meaning the horizontal and the vertical motion in these problems. And we're going to separate them with one common trait. The common trait is time. Time is independent of direction. The time it takes this one to fall on the ground was the exact same time it takes this one to fall on the ground. So time is the variable that will be in both x and y directions. But beside that, we're going to look at the x equations on their own. We're going to look at the y equations on their own because they don't affect each other. Last thing about this image. Last thing. If I wanted to get the overall velocity at any moment, look at my diagrams here. The overall velocity is represented by this third vector at each location. See the angled vector at each location that I'm kind of highlighting or circling right now? All of those angled vectors, to get them, does anyone have any idea as to how we could calculate them? Or what are you thinking?
Find the x displacement and the y displacement, and then you use what you're learning from the vector.
Very, very close. Moro's exactly right, except he messed up one word. One word. He said you find the x displacement, you find the y displacement, and you use what we did with vectors to put them back together, which is right, but one word is not right there, Moro.
I was going to say something about angles.
He said displacement, right? And what was my question about? Velocity, my question was about. Remember I said, how are we going to calculate the overall velocity? Because think about it. If I'm traveling to the right and I'm traveling down at the same time, then I must have velocity at an angle. This is my overall velocity here. So for these problems, what we're going to do is we're going to notice that again, just like earlier with vectors, objects have x velocity, they have a y velocity, and then how are we going to get the overall velocity? What theorem are we going to use based on my diagram I just drew there? What theorem will it be? Pythagorean theorem. Okay, that will be the overall velocity. So we're going to see this happening a lot. We can say the following here. Okay? Vx squared plus Vy squared is equal to V squared. Again, this is Vx, this is Vy, and in red is V. That is going to happen a lot. And the other part we're going to notice is that we're also going to always be searching for an angle theta. And that angle theta will come about from this trig ratio. Oops, I'll actually just write it out the first time. Again, that's Vx, that's Vy, and that's V. So where do I get this ratio? Because it's opposite over adjacent. Vy over Vx. I'm putting absolute value here. We'll discuss more about why that is in a little bit. I don't want to get too far ahead of myself. Okay, I'm putting absolute value here for a reason. Okay, so throw that around your fraction, please. So we're going to be seeing this over and over. Let's take a look at one example to start. It'll help us to see an example first. So a bridge is 300 meters above a river. Tom Cruise jumps off the bridge to avoid a sticky situation he's gotten himself into. I'm thinking of like those Tom Cruise movies where he's like always Mission Impossible. He does all his own stunts. He jumps off the bridge by running off the edge in a horizontal direction. He does not leap. He just runs off the edge of the bridge. Like somebody's chasing him and he runs right off. Now, if he hits the surface of the water after a horizontal displacement of 50 meters, what is the velocity with which he jumped? Now, the first thing for all of these problems, the best thing you can do, think back to problem solving from last chapter. What did I mention you should start with? Start with always. Listing the givens. Very good. Now, in these problems, givens might be nice to draw in your diagram also. I would recommend that your givens, which is the first thing you do, actually show up in the diagram. So here's my diagram, and it's going to never change. My diagram will never change for these problems. For something from a cliff, or from a bridge, or from a building, here's my diagram. And that's it. And I make a point to say this is always my diagram because every problem in physics can be modeled. What do I mean by that? Well, we launched this projectile from here a moment ago, right? We launched it from here, and it fell toward the ground. It's the exact same thing as if Tom Cruise is running off of a bridge, and here's Tom Cruise, and he's running off of a bridge with velocity initially. And then Tom Cruise will follow this path toward his probably demise. No, he never dies actually, so he'll never die, yeah. Toward that location right there. And we know that this is 50 meters. That's a whole other thing, yes. Let's make believe he's not into Scientology anymore. I made these problems before, that was a big thing, I know. The bridge is 300 meters above the water level. So we label that in our diagram also. So here's my diagram, but you know what? Write yourself a note on the side. If a hunter shoots a bow and arrow, if another hunter shoots a rifle, if Morrow pitches a baseball, if, I'm just thinking of something that's a pitcher, like in general, all these situations are exactly this. Because if I launch a bow and arrow, if I throw a baseball, if I shoot a pellet from a gun or an actual bullet, what's going to happen? It's going to start at some height, and what is it going to do eventually? Where is it going to most likely end up? If it doesn't hit something, it's going to end up on the ground. Or maybe the catcher is here, right? Somebody throws a pitch, the catcher's waiting for the ball. Well, the ball started up here, right? The pitcher literally releases the ball here. And yet, the ball lands down here in the strike zone. So clearly, even with baseball, even with something you think has no drop to it, the ball or the object definitely drops. So I like to generalize all of these problems like this. This is my diagram. It looks like a cliff. There's no bridge here. That may be a little artistic part with the water, right? So you can see water, but it doesn't matter. I can put this as a straight line, and it's the same thing, water, ground, whatever. Maybe this is where the catcher is, and there's a person catching the ball. Who knows what it is? But the problem can always be modeled this way. So, for all horizontally fired projectiles, this is your diagram. Again, for all horizontally fired projectiles, you can use this diagram. And we model all of our problems this way, that are horizontally fired. Can somebody again explain what I mean when I say horizontally fired? I keep saying it on purpose because it's really important here. Horizontally fired. How can it be differently fired? How can the firing be different, Nick?
You can fire vertical and down.
If you fire vertically up, vertically down, very good. Or
It could just be dropped.
it could be dropped, good. Or it could be fired at an angle. All of those scenarios are different than the one we just stated. So what we're going to do is in this course, for the most part, is we're going to classify problems. We're going to categorize them so that we have a general consensus as to how to begin the problem every time. You want to have these what I call under your tool belt, right? Your tool belt of problems. This is one of the types of problems here that we're going to look at. Now, let's get back into the problem itself. The given information we've drawn on the diagram already. We're looking for V0. That's our unknown, our desired variable. What's the one other piece of info that I haven't drawn yet, but we do know for all these problems?
The vertical acceleration is minus 9.181.
Very good. The acceleration in the y direction, in the y direction is going to be negative 9.81. Now, by the way, this is trivial, doesn't matter. I'm going to drop the 1 from 9.81 from now on. Only reason being, I didn't realize on your formula sheets it said 9.8. It doesn't use 9.81. I was in high school, we use 9.81, which is more precise. But gravity has a tendency, books have a tendency to round gravity to 9.8, or 10 sometimes. 10 is only used on like the subject test for physics to make numbers easier, because there's no calculator allowed in the test. If you take the subject test in physics, the SAT one, you can't use the calculator on it. So they make gravity 10 for that reason. But so you're aware, I'm going to drop the 1 at the end from this point on. I didn't do it early enough, I apologize. Just bear with me with that, okay? That is the acceleration. And notice what I put here. What is that subscript? Can anybody, it's tough to read.
Why?
Why? Because I want the acceleration vertically. The acceleration vertically. What's the acceleration horizontally? What did we say for these problems? 0. We are assuming there's no air resistance. Okay? There's no air resistance. So, let's take a look at this problem now. We've got our diagram, that's the beginning part. That's probably the most important part. But now what we do is we create 2 columns. I have a tendency to make my x column not as wide as my y column because there's not as much math going on and lengthy equations. So I don't make it split down the middle. I usually put this over here. This is a great technique for organizing your equations. It really helps a lot, especially for those that like organizational tools. For those that struggled on the vector stuff, when you come see me, I'm going to show you a table method that I kind of went over in office hours because some really still struggled on the test. Not everybody, most did pretty well, but there were a select few that struggled with vectors. We'll do something like this with vectors in office hours to help you organize your ideas. So for this problem, what I want to do is I want to list the equations that I could use. Well, if you remember, we have 3 main equations. We have this one. I'm going to put them at the top. That's the first one. We've got this one next. And then we've got this one last. And these are all on your formula sheet. And by now, some of you probably have them memorized, some may not. Okay, at some point, I promise they will become memorized just inherently from doing enough problems. So those are my 3 equations. And those are the 3 equations we started with. If we're moving, though, in a vertical direction, instead of calling it x, I'm going to call it y. I'm going to call the variable y. So in the x and y direction, we have to think about what equations we could use. Well, people, in the x direction, what did we say was 0 in the x direction always? What was 0 in the x direction always? Acceleration. So take a look real quick. Drop this off. Drop this off. Drop this off. Because acceleration doesn't exist in the x direction for projectile problems. So tell me, which of these 3 equations is actually meaningful still? Which has some meaning to it, Juliet? The first one. Juliet, want to answer the follow-up question? Why don't the second 2 have any meaning to them?
Because it's just like 2 variables, the velocity and the initial velocity.
So the initial velocity is equal to the final, or the velocity at other time. This tells me the initial velocity squared is equal to the velocity squared at some other time. Why are these equations absolutely correct but not useful? They're definitely correct. Why are they correct, and then why are they not useful?
Because there is going to be a change in the excuse me, sorry. Because, just because of the change in distance, there is going to be a change in velocity.
Careful. In the y direction, remember, velocity changes, we said. But what's the acceleration in the x direction?
0.
So if acceleration is 0, and acceleration is defined as the change in velocity, what can we conclude? Louder. There's no change in velocity in the x direction ever. Which is why these statements make sense, but they're kind of trivial. It's saying the velocity to start in the x direction equals the velocity at the end in the x direction, squared for both. Or the velocity in the beginning equals the velocity at the end. In the x direction, these are true. So in the x direction, we're only ever going to use this equation right here. Now, because I'm in the x direction, I like to use subscripts, and it will help. So instead of v0 here, let's call this v0x, or vx0. Your book does vx0, I do v0x. It doesn't make a difference. Okay? I'm going to put a little extra subscript, though, as an x there. Again, I'm putting an X right here to indicate the initial velocity in the X direction. Now, vertically, all three of those equations can be used. Because in the vertical direction, what do we have? What's that one word that we do have in the vertical? Acceleration. Yeah, acceleration. Only in the vertical direction, negative 9.8 meters per second squared. So what we can notice here is that we have a choice, right? We've got an option. Now, we've got an option, but our options are limited based on the givens. So in the y direction, list your givens, please. List the given values you know in the y direction. And you can do that from your diagram to help you. But in the y, I didn't list them in the x direction because I'm always going to use this equation in the x direction. It's never going to change. So I didn't have to choose an equation. But because I have to choose one of those three equations in the y direction, I will start by listing what I know. So give me one piece of information that I do know in the y direction. One piece of information.
The initial height, so x is 0.
So what's the initial height? What are you going to call it?
0 and then negative 300.
Okay, so watch what Jack is doing. He's calling the starting point 0 and saying it's going to land 300 meters below. Anyone have another? It's correct. Anyone have another way we can write this? Janisi.
We can say y naught is 300 and y is 0.
So either way works, but you need to be consistent. Okay, so if you're going to use this arrangement, you need to use 0 and then negative 300. Or you could say it starts at 300 and it ends at 0. But in either problem, it won't matter. Because again, we have y and we have y0. Right? We've got y and y0 in both spots. Or here we have delta y, which is y minus y0. So either case, we're going to have this idea. And if I do y minus y0, it's going to be 0 minus 300, which is negative 300. Or negative 300 minus 0, which is still negative 300. So either you choose this way or you choose this way. I happen to choose, just so you know from my notes, when you do it later, I chose this way here, where I started at a height of 300 and I ended what I'm calling the ground level. Okay, and I do that only because sometimes it's easier to think of the water level as sea level or ground level as 0, and then give this initial height of 300. But if you want to choose this way, it is absolutely fine, you can. There's nothing wrong with it. My question though now is this: what equation can I use, or what other information do I have or not have right now? What are my other givens? George?
Oh, you have acceleration at negative 9.8.
And what other piece of information? I've got one other piece. Maura?
What you don't have is final velocity.
We don't have final velocity. That's unknown, I agree. In the y direction and in the x both. Well, in the x we'll talk about. Justin? Horizontal displacement goes over here. Yep, I like that as 50. And the starting point was 0 for the horizontal. But what else in the y direction, Vin?
You know the initial velocity is 0.
Can you explain that, Vin?
Starting at the top point, like it's at the moment stop before the acceleration starts.
So what Vin is saying, if you think about a projectile when it's launched, when it gets to the very top, it stops until it starts to fall back down. So the problem that we're looking at right here, right, this launcher is launching only with x velocity. So it's like the second half of the parabola. Think about our problem here, right? This is the second half of the parabola. And as Vin noticed and mentioned, he said, well, at the apex, or at the max height, the object isn't moving vertically. It's only launched horizontally here to start. And then it starts to do what? Pick up vertical velocity on the way down. But to start, this is 0. Circle this, asterisk this, right here. This is the most important part for horizontally fired projectiles. V0 in the y direction is 0. Okay, that is huge. I don't know if you need to put stars around it or something, but please do it in your notes. That's so important. And this is always the case for an object that's starting at max height and moving like this, or just simply fired horizontally. Right? Starting at max height, if I drop it, or if it got up to max height and we start the problem from right here, and then it continues the rest of the way, this is true for those scenarios, or being launched horizontally. Now, with that said, our goal is to figure out the initial velocity in general, which we don't know. But I do know the fact that, hey, the velocity in the x direction is the initial velocity. That's what we're looking for in this problem. Our goal is to figure out how much it's launched with in the x direction. So our goal is to figure out this quantity right here. So we need v0x really, which is what we're looking for in this equation right here. We've got x is 50. So take a look at the x for now. Please look up. Look at the x direction. This 50 goes in here. This 0 goes in here. This is what we're looking for, which is this variable right here. So if we're looking for this, then we've got this and we've got this, and we're looking for this again. What else do we still need? Time. So write this down in big letters. Time is your linking variable. Time is your linking variable. Because it links the x and y directions together. It links them together. And what I mean by that is we can now say, there's not much I can do in the x direction, unfortunately, because I have too many things unknown. I'm missing both v0 and t. Right? If I were to plug in, just so you can see what I have here, and I normally wouldn't plug in numbers, and we'll talk about that, why that is. Here's what I've got. That's the equation in the x direction. 50, right? 50 goes in for x, 0 goes in for x0, and I'm missing two variables. Two variables I cannot solve with only one equation. That's why you learn this in Algebra 2. So I need a system. I need a second equation to make this work. So I'm going to move into my y direction. Now in the y direction, I don't know velocity in the y direction at the end, and I don't know time. Those are both unknown. Both of these variables are unknown. Does the problem ask me about the velocity in the y direction? Do I need to figure it out? Does it say find the velocity at the end of the problem? Or find the velocity upon impact? It only asks for the velocity where? Where? At the?
Release, like when he jumps.
Yeah, when he jumps off the bridge. That's the only velocity we care about. So our problem is asking us for this right here. We don't care about this. It's not given, and we're not asked to find it. So, as a result, this is not important, which means we can rule out the bottom two equations already. Go back up to your three equations up top. I'm ruling out the bottom equations because, again, I'm not asked about the final velocity at all. I'm not asked about the velocity 5 seconds into the problem in the y direction. I'm asked about the velocity at the beginning, which is only in the x direction. So that means I only have one formula to choose. So I'm going to choose y equals y0 plus v0 yt plus 1/2 at squared. And I'm starting to use subscripts everywhere, if you notice. Subscript right here. Subscript right here. That's a sub y. This is v0 sub y. Okay, because it's the velocity initially in the y direction. The acceleration in the y direction. It's important to specify in these problems now. So what are some things we know? I'm going to use the approach, I'm going to cross this off, not to confuse anyone. I'm going to use the approach that we start at a height of 300 and end at a height of 0. So I can automatically already say that this is 0, and I can also say that this whole thing is 0 right here. Take a look at what I've crossed out. The final height is the ground, which is 0. The initial height, well, that's 300, so we're going to use it. The initial velocity, as Vinny told us a little while ago, is 0 in the y direction. Again, what we just put these stars around, because it's only fired horizontally. It's only fired horizontally. So that drops off. AY is negative 9.8. This is known. What's the only unknown in this equation that's left? What's the only unknown? Time, t. And then we'll plug it in over here and be able to get VOX. So, I want to point something out. Big, big, important thing. You can either plug in numbers now. You can plug in negative 9.81 or 9.8 and plug in 300 and solve for t and get a number and get the time. The problem doesn't ask me for time anyway. So I can also just solve this algebraically with variables and plug that expression in over here using substitution method. So watch what I'm going to do here. I'm going to write what it becomes. This equation becomes 0 equals y0 plus 1/2 ay t squared. That's what it becomes. And then if I solve this for time, I'm going to subtract y0. I'm showing the steps today. I'm not going to show these steps ever again. I'm then going to double to get rid of the 1/2. I'm then going to divide by a. And then finally, to get rid of the square, I'm going to take the, And normally when I put a square root, what do? What do I put out in front of it? But do I have to here? Because time cannot be? Okay, so I don't care about that. So this is my answer for time. Sure, by all means, plug in. You will get, of course I didn't plug in to get it, because I didn't care about it as much. Yeah, so I didn't plug in my numbers. But if you want to know what the time is when it impacts the ground, plug in. -2 times 300 divided by -9.8. That number under the square root. You'll get a time. I don't care what that time is though, because the problem doesn't ask me for time. So instead, what I do is this. I take this expression and I plug it in right there. Because again, I'd rather solve with variables. So instead of 50, I'm going to make this back to x, so I have all variables. I'm going to call 50 x again. I'm going to cross this off, this 50, and put it back as an x. This equation then becomes x equals v0x times that whole quantity. And that's my equation. And what was my goal? My goal was to find v0x, the velocity in the x direction. So just divide by this giant square root looking thing here. Just divide by the square root, please. So this equation, as a final answer, becomes this. v0x equals x over that entire square root. This is my final answer. On a test, technically speaking, you get to this point, it's right. Now, if you plug a number in and you get a wrong answer, I might take off like a 1/4 point or 1/2 point. Now, a couple of you saw that on your test, this one, because you solved everything correctly and then somehow made a mistake in your calculator. If you can get to this point, you've done the problem. On an AP exam, a lot of problems don't give numbers. And they'll say, find the solution in terms of your other variables. This is velocity in terms of horizontal displacement, vertical starting position, and vertical acceleration. That's this answer. Velocity as a function of those three. Why am I pushing you to solve with variables, do you think? Before I get to the question. Why do you think I'm pushing you to solve with variables? What's the power to this solution method? It's powerful. It really is powerful. Why, Jack? What do you think?
Since you never round, it's like exactly correct.
Correct. I didn't even think about that. Very good, Jack. We're not rounding time as a decimal, so the answer will be exactly correct. Very good. I didn't even think about that. There's a second reason to it. A second reason. Seb.
Is it repeatable for any question that's
Seb, there it is. This solution is a generic solution for all problems that are launched horizontally when you're trying to find the launch velocity. This is a generic solution. So I could say now, ready? What if Tom Cruise lands 75 meters from where he started? Well, instead of putting a 50 here, what do you put in? 75. What if I make it even annoying like last time? What if gravity feels now air resistance and gravity is half of gravity? I change this instead of 9.8 or -9.8, I make it -4.9. What if I say the cliff height or the bridge is not 300 meters, but 500 meters? Now y0 becomes 500. Do you see what I mean? How I can now vary all of these things, which means we call them parameters. X, y0, ay are parameters. We can vary those parameters and get different results. Would you do this by hand? Probably not. You would use a computer program, and you would write a conditional statement, and you would use loops, and you would use what are called vectors. And those vectors, or they're called arrays in computers, you would consistently change one of the variables. Then you would run it through the calculator program, and it would spit out 6 different initial velocities based on the 6 different x values, or changing each one. The number this turns out to be is 6.4. Okay, 6.4 meters per second. What you're going to notice is that at the end of the notes, we're not even close to done, but at the end of the notes, your homework has two types of problems. The ones that don't have the asterisks, you can start tonight. Okay, you can definitely start the ones without the asterisks. I've already put it up on Moodle as well. Again, tomorrow and Wednesday after school office hours, please. If for some reason your project written part isn't in, and it's not in still today, it's already late 2 days, get it in today, or you're going to lose a lot more than you'd want to on a project grade. I suspect everyone's is in, but I'm just saying that in case.